Okay, everyone, I think we'll get started. Welcome to this lecture. This is the final lecture of the course, Introduction to Differential Physics, Part 2. So let's get straight into it. We all know, like I said, the last lecture. So we had the lecture before this was the first part 1 of the introduction of to differential physics. And so this lecture, we're just going to develop some of those ideas that we've learned about in the previous lecture. So how's this lecture going to look? So we're just going to recap some of the ideas. So what differentiable physics is, these kind of hybrid scientific machine learning workflows that we learn about. And then I'm going to try and code a very simple example of a hybrid approach in PyTorch, just to show you how easy it is to write a differentiable kind of physics algorithm. And then I'm going to go into some more complex ideas on how to code hybrid approaches, and in particular, how to use a hybrid approach for inverse problems. So last lecture, we looked a lot about simulation. So this lecture, we're going to think about inverse problems and maybe even discovering equations as well using these hybrid approaches. And that will lead us onto neural differential equations, which is this kind of whole field that brings together very closely differential equations and neural network architectures. And the very kind of last result I'm going to show you is you can actually think of neural networks as solving PDEs in general. And this is a really cool idea that really marries the field of scientific computing and machine learning together. So that should be a really nice summary to the course. And then I'll give you a quick kind of general trends of what I think you should take away from this course, and then that will be it. So there's a lot to cover, and hopefully we can get through it. So okay, so let's just recap. So what do I mean by a hybrid approach? Well, so can anyone define it for me? What would you say is a hybrid approach from the last lecture? What's the general idea? I mean, I've written it on the slide here. So can anyone just say it in their own words?
Instead of like doing purely like machine learning approach, doing the traditional finite element of finite method, we can just replace part of the trading algorithm with the neural network in order to probably speed up or to reduce the computational cost of the algorithm.
Yeah, exactly. So to summarize, we have traditional algorithms like finite element, finite difference simulations. And what we want to do is put a neural network or some machine learning component inside of that, specifically inside of that algorithm in a very specific part, rather than replacing the whole algorithm like with a single neural network, which is learn in a very data-driven way. And so why do we do this? We do this because, well, we know using neural networks has a lot of advantages. They're fast. They can represent very complicated functions. But as we've seen through the course, there's a lot of limitations as well. So they need a lot of training data. They can be very hard to interpret. They can be hard to optimize, and they don't generalize very well often. So if we take this hybrid approach where we're blending in machine learning, the parts that we either want to speed up or that we're not sure about in our traditional algorithm, generally this could perform much better than doing a more naive data-driven approach. Right. Yeah, and so this is the slide we keep coming back to. These hybrid approaches are just one way of thinking about putting scientific principles into machine learning algorithms. So the other way is to do just change the loss function or to change the architecture. Okay. Yeah, and so we talked in depth about this hybrid Navier-Stokes equation solver. And so the idea here is we took a traditional algorithm. This was just a Navier-Stokes solver based on operator splitting. And it's basically a time-stepping algorithm where you start with your initial flow field and you just take time steps of your solver. And we realized that if we have a very coarse grid, so a very low fidelity solver, the solution is not very accurate. It doesn't model the high frequencies or the turbulence in the solution very well. And so what we said, we would put a neural network inside the inner loop of that solver, and we would get it to correct the previous or we would get it to correct the low fidelity step at each time step. And so this neural network is interleaved inside of the traditional solver. You can see it in the code here. We take the output of the solver and we correct it inside that for loop. And we hope that if we can train the neural network, the solver will be more accurate, but still fast, because it only needs a coarse grid to model the solution. And we asked the question, how do we train these hybrid approaches? Well, what we realized, and this is a really important concept that, like I said, underpins pretty much all of scientific machine learning, is that auto differentiation allows us to differentiate arbitrary programs and not just neural networks. So we could think of this whole hybrid function, which takes our initial state and outputs our final simulation state. It's just a flexible, learnable function that we can differentiate through using auto differentiation. So we can create a loss function which matches the outputs of this function to some high fidelity simulations, and we can just differentiate through the solver to update the weights of the neural network. And so this is a really important concept to grasp. Yeah, and so this was the result. So if we add that hybrid neural network in, we get a much better improved accuracy of the simulation, but also it takes a lot less time than if we did the high fidelity solver using a much finer grid for the simulation. Okay. So that's the recap of the last lecture. Like I said, I'm going to now extend these ideas and go to more complex hybrid algorithms in the rest of the lecture. But before I get to that, I want to give you a really quick example coding of a hybrid approach, just to show you how easy it is to write a differentiable solver in PyTorch and to differentiate through it. Okay, so we're going to switch to switch my sharing screen here. So just give me a second. So what you can see here is a Jupyter Notebooks. And so I'm just going to be coding a few lines of this example. So we're going to pick a problem. You can pick obviously any physics problem to differentiate through. I think this is a really fun problem. And so this is, hands up who's seen this video or this idea before. It's around social media a lot. So the idea is that you're dropping a ball here from some high point. And we're just going to say it's just in the coordinate space, it's a 0, 0, just to make it easy at the origin. And then we're going to drop it to some lower point. And the goal here is to find the path at which the ball takes the least time to arrive at the final destination, so this final point. And so you could think of different paths. You could think of like a linear path or one where it drops really quickly. And it turns out that the one in the middle is like a special curve. And so does anyone know what the actual type of curve this is? Yeah? Yeah, it's a cycloid. So this is the shape that if you put a pen on a bike wheel, that would be the shape that the pen traces out over time. So we're not going to assume that we know this function, and we're going to try and learn it instead. So we're going to say, why not have a neural network here, which is just a function of x. So it takes the x coordinate and predicts the y value. So basically, it's just defining y as a function of x. And this function has some learnable parameters theta. So we're going to say it's a neural network function that just approximates this cycloid curve. Does that make sense to everyone? Okay. So if we're going to train that neural network, we need to be able to compute. What we want to minimize is the time it takes for the ball to travel to this point here. So what we need to do is we need to take that curve and we need to integrate the time or the velocity of the ball as it's traveling through that curve to give you your final time. And then our loss function is going to minimize that curve, minimize that time to learn that curve. It's going to look, so the loss function is a function of the parameters of the network. Is going to learn those parameters. Okay, so I'm not going to go through the physics model in detail. It's trivial enough to derive an expression for your capital T here is the total time it takes for the ball to travel. And so I'm just going to skip to the final expression. So it turns out it's this integral if y here is y as a function of x is the curve that is traveling along, I just need to integrate y with respect to x, or this functional expression, and it contains a derivative of y here. So this is the thing that we want to integrate to get the travel time. So as I said, what we're going to do is we're going to say y of x is approximated by a little neural network here, n of x with some free parameters here. And so we just very simply substitute this thing into our travel time equation. And then immediately this is our loss function that we're going to try and minimize. So we're going to try and tune the weights of the network here to minimize the travel time of the ball. Does this make sense to everyone? Yeah? Okay. So it's kind of an interesting loss function because it contains an integration. So we're going to have to think about how to do that. And it also contains a derivative of the curve or of the network. And we're going to find that we can very easily incorporate that into our when we're using PyTorch in auto differentiation. So okay, so yeah, this is the expression for the true solution. It's a cycloid. It's a parametric equation. So if you're interested, you can read this blog post, and it goes through the whole derivation of the solution. So it's okay. So with that, I'm just gonna talk you through the code. So what we're going to say is we're going to define our neural network in PyTorch. So this is just a standard fully connected network that we're initializing here. And so I'm going to have to write this forward function. So remember, the network is just approximating y as a function of x. So we have x as a coordinate here. And I've also got the final point that the ball is going to end up at, just as an extra input to the network. So we're actually going to do something a little bit more clever than just have the solution be the output of the network. I'm going to have the network as part of an ansatz. So I'm actually going to say that my solution is going to be approximated by a base model. So I'm going to say, okay, we're just going to say we're going to start with a straight line as our base model, and we're going to get the neural network to learn a residual correction to that linear model. This is a bit like those hybrid residual methods I was talking about the last lecture. So we're gonna say the solution is like the linear model plus a flexible residual model. So let's do this. So we're gonna say y linear here is just a linear model. So we know the ball starts at the origin. So this is just the gradient times by the x value. And then we're going to say the network learns a residual. So we're just going to pass x through a neural network. So we're going to say self.fcs here, x. I'm also going to normalize x with respect to x2, just because that's good practice of neural networks. So we can do this. And then we're going to pass it through the hidden layers like this. And then the final layer like this. So we've got a couple of hidden layers in the final layer. Cool, and then our final model is just going to be the linear model plus the neural network output. Does that make sense? Yeah. So there's one other trick that I'm going to do. I know that the ball has to start at the origin and it has to end at x2. So the residual correction that the network learns at those 2 points should be 0. We don't want it to add anything to the linear curve. So there's a trick that we can do to make sure that we have that constraint in basically our initial condition inside the ansatz. And so we just times our output of the network by x or tan hx. And you can see when x is 0 here, this is going to be 0, and it's going to force whatever the network is, this whole thing is going to be 0. So we do this. Tan hx, and we want to do the same thing with the x2 as well as 0. So we do torch.tan hx minus x2 like this, and then we times it by y. So this is just going to make sure that this residual is 0 at 0 and at x2. Let me just have a look and make sure this is correct. It seems good to me. Yep, I think that's okay. So we'll run that. And so then what I've got here is just a basic training loop. So I'm initializing my model. I've got a for loop where I'm going to optimize the weights of the neural network. This is very standard neural network training loop, nothing fancy here. Going to use an atom optimizer to learn the weights of the network. And so the only thing that I have to do is compute the loss function now. So I'm going to sample x along from its starting point to the final x2 point. And I'm going to do this because I need to evaluate this loss function in the integral. So I'm going to discretize the integration, and we're just going to use the trapezium rule to approximate this integral. So we're going to sample a bunch of values of x, use the trapezium rule to evaluate this function, the integral of this function in the middle. So I've got my values of x here. So the first thing we need to do is to evaluate this inner function here. So the square root of these gradients. And so first we need to pass x through the model, right, that we just defined. Then remember in the loss function, we need to define this gradient here. So we just use autograd, right? This is the power of auto differentiation. We can differentiate whatever we want, basically. So we say dy equals torch dot autograd dot grad. So we want y with respect to x. We want to remember this is a Jacobian vector product or vector Jacobian product, as we talked about. So we're going to do ones. Pass ones to that vector product. We're going to make sure that we create the graph so that we can differentiate through it again to update the weights of the network when we do the final gradient descent. So that if you think about how we were training pins, this is actually kind of similar ideas as pins, right? And then we're going to take, we know that the output's a tuple, we're just going to take the first value. Okay, so this is our derivative. And then we're going to compute this inner function of that integral. So it's the square root of 1 plus dy squared, like this, divided by 2 times g times y, I believe. So I'm just going to check that. So 1 plus the gradient squared divided by 2 over gy. So gradient squared, 2 over gy, like this. Okay. And then the final thing, we need to integrate this function. So as I said, we're just going to use the trapezium rule to do that. And thankfully, Torch has this function that I have in this other tab. So it's called trapezoid, where you pass in your values of your function, your values of x, and then you just tell it you want to integrate along the first dimension. This is the first dimension of the arrays. So this does that integration. So we can call this value t. This is our final time. Okay, so we've gone from x to the final value of t, and we've got a nice computational graph that we're tracking. So then we can just pull backwards on t to get the derivative of t with respect to the weights of the network. And PyTorch will just do that for us. We don't have to worry about defining those gradients ourselves. So then it just becomes as simple as doing t dot backwards. T dot backwards. And we want to make an optimizer step. Just as you would do when you're training a normal neural network in PyTorch. Does this make sense to everyone? Any questions so far? Yeah? Okay, so let's see if it runs. No, so we need to pass x2 and x and y2 to our model. Okay, perfect. So let's just see if it seems working. Right, so I've got two plots here. So the first is the prediction of the neural network. This is the y function of x that it's learning. And then our true solution, so our cycloid. And remember, as I said, we assumed that the solution was linear plus a residual correction, and we constrained that the solution was going to be the residual that the network learns is going to be 0. So it's always going to be passing through the x1 and x2 points. And you see there's a little bump here, which is the residual that the initialized neural network is suggesting. We can also plot the velocity of the ball as it goes down this line. So yeah, you see it training. So it's starting to lower the travel time and explore different solutions, and eventually, after a few thousand steps, it gets to a good approximate solution of the curve. So yeah, this is just a quick demonstration of defining a physics model, defining a flexible learnable component of that model, and differentiating through the model to learn that component. Yeah. Okay. So let's just switch back to my slideshow. Okay. Right, so we coded a simple example, and so now I'm going to talk more about some more complicated hybrid flows. So in particular, we're going to think about how we would use a hybrid sine-null approach to carry out inverse modeling. Okay, so before we do that, we just want to think about this Navier-Stokes hybrid approach that we've already looked at. And I think it's clear that there are actually many ways that you can put a neural network or some learnable component into this workflow. And it doesn't just have to be a correction like we have here. So we could put it in many other places. Can anyone suggest where else we could put it? We talked about this last week. Where else might be interesting to put like a learnable component, either to speed it up or improve the accuracy of the solver? Yeah, that was one idea from last week. Was this matrix solve can be very expensive if you have a really large grid that you're discretizing the solution over. Yeah, so you could have a neural network here which maybe initializes that matrix solver algorithm or preconditions it somehow. Yeah. Okay. So what interesting observation here is, if you think about the traditional algorithms that we use, so like simulation codes, data assimilation codes, control algorithms, equation discovery, a lot of these algorithms actually just boil down to an iterative algorithm. And so what do I mean by that? It basically means you have a for loop with a lot of complicated code in the middle, and it's just iterating through that for loop to compute some iterative solution. And so we define a broad class of hybrid techniques, which are called in-the-loop methods. Very simple idea. We're going to add some learnable component in the inner loop of that traditional algorithm. So once you realize that many different algorithms have these, then it's really interesting to kind of study these types of hybrid methods. Okay. So with that in mind, let's think about an inverse problem. And so this is the problem of X-ray tomography. So this is where, for example, we want to create an image of the brain or any part of the human body. And I showed this in the very first lecture of the course, actually. And so we have some X-ray source here, this star, and it's sending X-rays through the target, and we're measuring them on some screen. And this screen just measures the amplitude of that X-ray at that screen. And as it goes through the target, it's getting attenuated by some attenuation function as a function of space, right? So this is essentially the image of the brain. How light or dark the image is tells you how much the X-ray is attenuated as it goes through the material. So we know that the final amplitude recorded at the screen or the detector is just an integration of that amplitude profile in space. So we just integrate along the lines that the X-ray travels. And so the other way that these machines work is they usually spin the target around. And so what you have eventually, if you do that, you can see, imagine X-rays shooting out and recording their amplitude on the screen as it rotates around. You can see the data that it's recording, and it records these sinograms. And so these are just you can think of them as an image, where one axis is the angle and the other axis is the position along the detector. Yeah, so the inverse problem is basically, given this observations of the sinogram, so we're going to call it B here, can we figure out what the underlying image or the underlying attenuation profile is that the X-rays went through? So this is like a classic inverse problem. We have some forward model, which is this integration, and we have some observations, and we want to invert for the underlying parameters. Okay. So let's talk about like a traditional algorithm to solve this inverse problem. And we can solve many problems like this using gradient descent again. So we can just frame this as an optimization problem where we have some observational data B. Again, this is the sinogram here. And we have some forward physics model, and we want to understand what A is. And so we're just going to take an L2 norm and just try and minimize the difference between the observations and what the physics model predicts is by changing the value of by changing the input image. So let's just assume that the F is differentiable. And we know that most forward simulations are. If we just write them in an auto-differentiable language, we can get gradients. And so we define a loss function, this is the loss function, and then we do gradient descent to update the values of A. So we have to start with some initial guess of what the image is, and then it will slowly update to hopefully, if the inverse problem has enough information, it would give you the solution to the problem. Okay. So yeah, this inverse problems in general are much harder to solve usually than forward simulation. And the reason is because they can be very ill-posed. So what do I mean by ill-posed? Does anyone know?
No solution.
Yeah. So it basically means that the information contained in B is not enough to uniquely determine what A is. So there could be like a many to or one-to-many mapping of the solution here. And you can imagine that, like if you just had one detector here and one ray going through it, you wouldn't be able to figure out what the attenuation would be everywhere else. It would be really hard. And this gets harder when these sinograms or the observational data is very noisy. And it also gets harder, if you have not as many observations as you need. So yeah, one approach, which is very popular, is to add some idea of regularization. So by the way, as we're going through and explaining this traditional inverse algorithm, in your brains, you should be really drawing parallels to the way that we train neural networks. Because everything here I've said previously, when I'm in the context of how we train neural networks and how they generalize and how we regularize them, it's exactly the same framework. And the ideas can be, brought across the two fields to improve both fields. So this idea of regularization, for example, like L2 weights on neural networks, this is the same idea. It's just the thing we're trying to learn and not weights of a neural network anymore. So yeah, one idea for regularizing this loss function, we just basically say we want the solution, the output image here to be smooth, so the spatial gradients to be small. And so this is just a prior that we think is a good idea if we just want to have like human-like objects that we're passing the X-rays through. So you can see, for example, if we ran this inverse algorithm, it could give a very speckly answer. And if we had this type of regularization, it might remove the noise in that output of the inverse algorithm. So this is called total variation regularization. And there are many other regularizing strategies you can use. It's just one idea. Okay. So if I'm just going to write some pseudocode for this is going to be important when we start adding neural networks. What I'm writing here is a very basic gradient descent loop, essentially. So I start with my initial guess of what the image is, the solution. I pass that thing through my forward function, and I know for this particular problem, it's just an integration. So we have some numerical integration here. Then I figure out what my regularization term is. That's just a function that I'm applying to the image. I create my loss function here, which is the difference between my observed data, which is an input to the function, and my guess from my forward model. Make sure I have the regularizer. If it's written in a differentiation platform, use autograd to get the gradients of the loss function, then do a gradient descent step. So this should be very simple for you to understand. Hopefully. So yeah, and this is just written out exactly what I just said. Okay. So what we really want to do is we want to make this a hybrid approach, right? So we want to put some learnable components into this traditional algorithm, just like we did for the forward simulation for the Navier-Stokes solver. So what we're going to do next is we're going to think, where can we put ML into this that makes sense to either speed it up or to make it more accurate? Okay. So I've just drawn this out pictorially. Sometimes it's a bit easier to understand in a picture. So again, we start with our model, do some forward modeling, compute our loss function, compute our gradients, do this inner loop of the algorithm, and then eventually we end up with a final model. And our input is our real data here. So what I'd like you to do is just to find a neighbor, so someone you're sitting next to, and I want you just to have a quick discussion, maybe a minute, about where you think you would put a learnable component into this workflow. And there's no wrong answers. Actually, there are many answers. And so after that, I'm just going to ask a couple of you where you think you would put it. So yeah, please have a discussion. Okay, I think that's enough time to have a couple of ideas maybe. So anyone wants to offer an idea where you would put it into this algorithm? Or just a starting idea if you're not sure, it's fine. It's okay.
Like the obvious one is to replace the model by a level. Replace the model, yeah. And the updated model is just the stochastic gradient distance step. And as for in this case, we have synthetic data, so it might be a good idea to use GAN, like to do like game theory type of training.
I see. Oh, interesting. Okay, so you were saying one way might be to use a neural network to replace the forward modeling. And so what would that bring you? Why would that be useful?
Because like we can use because our updates, our training algorithm is iterative. Yeah. So like we can just use all the differentiation to do the gradient descent for this model.
Yeah. So eventually we are going to be using gradient descent to train this. We can actually do that with an existing physics model already, if that model is differentiable. I mean, we're already creating gradients inside this algorithm to get gradients. So, but one reason why you might replace this with a neural network is if this is very slow, you're going to run this in a loop maybe thousands of times in a standard algorithm. So if F is very slow, then that's very prohibitive. So this could be a very fast model. So yeah, that is a good idea. Another reason maybe you're not sure about the physics model. So for example, if you're not exactly sure where the positions of the detectors are, or the angle of the instrument, maybe you could treat something in there as learnable, for example. Yeah. Any other ideas? Yeah, go on.
So maybe there might be a network that's similar to the fluid flow problem. We can map the residual or the difference between what the model predicts and what the label is. Yeah. And then try to learn the difference. Yeah, exactly. So you might have here, like maybe at the output, you might have a neural network that takes the guess and does like a final correction to it, that outside of the inner loop, perhaps. Yeah, really good idea. Yeah. Any other people? There were some discussions over here, perhaps.
Anyone else? Yeah.
Can we replace the initial guess with this situation?
Yes. Yeah, really good idea. So these algorithms really depend on what your initial guess is. If it's close to your solution, they will typically converge. But if it's really far away, it can be really, really hard. And so there are actually quite a few, I would call more naive methods, where they just learn the direct mapping from this to this without any of this algorithm in the middle. You just have a neural network which takes B and gives you a guess of A. So we could have that at the start of our workflow. We could say a neural network takes B, gives us a starting model, and then maybe we'll improve that iteratively afterwards. Yeah, so it's a really good idea. Okay. So I'm going to show you one that I don't think maybe you didn't think of, which is we're going to think about this gradient descent step. And so when we do gradient descent, we say we're going to evaluate the gradient of the loss, and we're going to take a step in that direction. And what we really want to do is explore the parameter space until we find a minimum of the loss function. But we know that loss function is going to be incredibly complex, especially if the problem is ill-closed, and it's going to have lots of local minima, etc. So the gradient is not perhaps the best idea. So what if we actually try to learn a better step to move in the gradient space that gets us closer to the solution quicker? So this is the idea, that we're going to have a neural network here which is going to correct those gradients of the gradient descent. So it's going to take, what's it going to take as input? Well, it can take a lot of things actually. First, it would just take the gradient itself as like an initial guess of where it should step in, I guess. And then maybe it could take other stuff as well. So for example, the model, the observational data, the value of the regularizer, everything that has inside of that inner loop, all the variables that are available, it could just take as input. And then the output is going to be a new prediction of a step to direction in the parameter space, and we're going to take that step. So it's kind of similar to what you were describing, where you would have a neural network to correct the image. It's kind of the same idea.
So this is like adaptive learning, like
right. So this is yeah, you could think of it as adaptive learning. I'm going to argue that it's a bit like learning to learn. There's analogies in neural networks here, like with meta learning, for example. Yeah, we'll get to that. So. Okay, so how do we do that? How do we rewrite our code? So it's actually incredibly simple. We have this is our original traditional algorithm, and we're just going to add a single line in our pseudocode, which, yeah, we have our gradients that are computed by AutoGrad. We just pass them through a neural network. We give it some other information that we have, you know, the starting guess, the observed value, the predicted values, perhaps the regularizer value, and then our weights of the network. And then that's our new algorithm, our new learnable hybrid algorithm. Okay. So yeah, the algorithm is very similar. We're just changing the gradient descent step a little bit here. Cool. Yeah.
Basically replacing the AutoGrad by neural network?
We're not replacing it. So we're still using AutoGrad to get our original gradient of the loss function. We're just going to pass that gradient through a neural network to update it. So it's going to say, given this gradient descent step, a normal gradient descent algorithm would use, what's a better one to take? And okay, so you're going to argue, like, how on earth would you learn that? So that's what I'm going to try and describe next, is how we can train such a neural network. Yeah. So yeah, this line is still here, this AutoGrad line. Yeah. Okay. So yeah, how do we train this? This seems like a really complicated thing to train, like we're learning some part of a gradient descent algorithm. So let's just make it really simple. As I try to argue that this is a really complex function. It's got a lot of stuff going in, it's creating gradients, etc., etc. But at the end of the day, it is just a function that has some inputs, you know, and our inputs are our observational data and our starting model. And it has some output, which is our guess of what the solution is. And we could just treat that as a black box. That's just an algorithm. And we can use auto differentiation again to get gradients of the output with respect to its inputs. Hopefully that makes sense. Auto differentiation allows you to differentiate arbitrary programs. This is an arbitrary program here that has some inputs and outputs with some complicated thing in the middle. So what we do is we just put a loss function that tries to match the outputs of the algorithm with the true values, right? So the loss function we use is very simple. We just say, so h here is just the function, it just represents this function. So h is hybrid X-ray tomography. So it takes in my starting guess, a hat here, my observed data, and the parameters of the neural network. And then I'm just going to try and match that to what I know is the true solution. And I train this loss function with many examples of different solutions. So I'm going to give it lots of examples of different heads, for example. So this is just the training data that you need to learn it. You just need examples of inputs and outputs of the function. So this should hopefully would make sense to you. Any questions?
Is this going to outperform the conventional optimizer?
Right, well, that's the question. So as I said before, inverse problems are really hard to solve because they can be ill-posed, they have data in. And the loss function in the traditional gradient descent, in this inner function here, that the loss function is going to be very complicated, have lots of local minima. So it's not guaranteed that this is going to converge. And so what we're trying to do is design a better algorithm that will converge in more cases. And it's going to do it by learning from examples. It's going to use the information encoded in these example training data to fine-tune or specialize this inverse algorithm so that it performs best on this data. Does this make sense? Any questions? Yeah.
So I think for this to work, you have to assume that the topography of the loss function is somehow contained in the input parameters, which is the gradient, A hat, B hat, and regularization.
Yeah.
Otherwise, you won't be giving anything to your network for it to understand where it goes.
Yeah. So good intuition. I agree. Think about how the original gradient is computed, right? Just in the traditional algorithm, how do we know that gradient descent is that direction is a good direction to go in? It's based on our physics model. So our prediction B hat here is passed through our physics model. So this is why we know that gradient direction is a good informed direction to take in the first place. So we're just saying, maybe we'll just learn a correction to that. So we already have a lot of information in DA here about the forward physics model, about how close we are to the solution, etc. So I would argue that there is enough information to learn a better correction, perhaps, especially if you're training it with lots of examples in this outer loop. Yeah. So you could think of this neural network as it's like learning a prior. It's like, given all of this example data, I know in general that this is a good direction to take in the parameter space, given all these previous problems. Like, this has worked in the past, I'm going to do it again in the future. So it's seen lots of examples of these inverse algorithms operating, and it's realized you should go this way instead of this way, because in the past this way went better for this particular training example. Yeah. Okay. Right. So yeah, so this is the final chunk of code to actually be able to learn these parameters inside this hybrid algorithm. And this is just standard code for learning theta. It's you just make sure theta requires gradients, so we're tracking it in PyTorch, and then we just run a standard training, an outer gradient descent scheme. So we just take a bunch of gradient descent steps where we compute the output of the hybrid function. This is the guess of what the solution of the inverse problem is. We match it to what we know is the true value from our training data. This is our new loss function, and we get gradients of that loss function with respect to the parameters of the network, which is just an input here to the hybrid function. And then you do gradient descent on theta. So this is exactly how you would train a neural network. It's just the function here is not a neural network, it's like a hybrid function instead. Okay. So yeah, as you pointed out, you can think of this as like doing gradient descent on gradient descent. We have an inner loop which is doing gradient descent, and then an outer loop which is doing gradient descent on that to learn a good gradient descent algorithm. Yeah. So this in pure machine learning or deep learning, this is also known as like learning to learn. It's like a kind of a meta learning task where you're trying to learn like a good optimizer to train a certain class of neural network architectures. It's exactly the same sort of ideas. So we're trying to learn a good inverse algorithm to model a certain set of problems. So yeah, it's a really, really cool idea. So yeah, this is the paper that did exactly this approach that I was describing for these X-ray tomography problems. I'm just showing a single example here from the paper, and so we're comparing the ground truth with the traditional inversion and then applying this learned gradient descent. And it was just trained on lots of examples of human heads previously. And I mean, you can look, it's kind of hard to see the difference. I mean, it's one clear difference is this one looks a bit smoother than the traditional inversion. So perhaps it's learned some sort of like total variation regularization somehow, like similar idea. Perhaps it's not got as many of the high frequency features, but if they did compare it on across a whole test data set, and quantitatively it performs better than this traditional method. Yeah, you've got it. Say that again. What's the
How do you get the ground truth?
Yeah, so this is, yeah, it's a good point. So I'm not actually sure where this image was taken, but I imagine it was from a very highly densely sampled scan. They may have had way more detectors than they're using in the inverse problem to solve. Yeah.
But then what we're doing is basically do the traditional inversion and then try to learn that. Because you need a picture to start with. Ground truth.
Yeah, so this inverse algorithm doesn't start with this ground truth. It starts with an initial guess, which would look more like this. It's like a blurry image or something. Like maybe you just assume it's maybe a constant value to start with. So the inverse algorithm doesn't know what this is. It's just given the observational data from this. So it's given the sinusoidal, the sinogram that this image would have produced. So, and these are just two different approaches for solving that inverse problem.
Do I have another question?
Yeah.
It's like, is it like maybe similar method to learn the regularizer?
Yeah.
Like, probably for this one is because it's used for variation.
Yeah.
Regularizer is much more smoother than the one shoes and the stuff. But
yeah,
is it possible to learn the regularizer?
Yes. Yeah. So you're jumping ahead. So this is the next one, the next slide. So yeah, this is a really good idea. So yeah, to be clear, so the way we set up this inverse problem is we had a ground truth image that was maybe computed from a different experiment where we had like really a lot of detectors, or maybe it could even be, I don't think it is synthetic, but you could use a synthetic image if you want. Then we just pass that through our forward model to get some observational data. And so then we have that observational data, and then that's what we pass. We only pass that observational data into these two different inverse algorithms to get their predictions. Yeah. Yeah.
So this technique does not help us to get rid of local minima, right? Because we will just jump faster
Yes.
to the local minima.
It doesn't, yeah, so it doesn't change the loss function, the loss landscape of this inner gradient descent algorithm. But what it does do, it takes a different direction. So it doesn't have to follow the gradient anymore. It could go uphill if it really wanted to. If it's learned from previous directions that that's a good idea at that certain state of the inverse algorithm. So it might learn to like jump over a hill, or go completely reverse the gradient direction if it thinks it's important to do that. Yeah. Yeah. Okay. So yeah, so why not just have one neural network? Why not just go for it and put learnable components across many different places? So yeah, I think you already suggested when we're having that brainstorm, there are many other places you could put neural networks. So for example, we could think about a regularizer here, and we said that that was kind of an arbitrary choice. It depends on the problem, what we want to penalize in the outputs of the inverse algorithm. So in particular, we had this total variation regularizer here, and we had to times it by a hyperparameter lambda to balance the two terms as a loss function. This is the observational data term, and this is the regularizing term. So typically, the way that you would choose that is by running lots of inverse problems, tweaking it, and just doing a hyperparameter search. So you could just treat that as a learnable parameter, and it could learn it from the data. What's the best balance between the regularizer and the data loss to do that? And you don't have to change anything about the way you train the neural network or these parameters. It's the same training loop. You're just updating the gradients of this thing as well.
But in this case, it's still the total variation, right?
Yeah, still, yeah.
But if we want the sharpness,
yes,
or the rigid, then we need another regularizer.
Exactly. So then you can open this up and say, oh, actually, R here could be a function that's learned by a neural network, or it could be a bit more precise than that. You could say, I want it to be kind of like a total variation. So I'm going to take the spatial gradients, but then I might alter the gradients with some learnable corrections somehow, so that it doesn't penalize step changes that we know at edges in things, for example. So yeah, we can do that too. Okay, so yeah, just to reiterate, we don't need to change the way that we train the neural network or this extra learnable parameter. It's the same training scheme with the same training data. We're just opening up or making the underlying algorithm a little bit more flexible. And we can really do whatever we like. So yeah, so this is a really key idea. Traditional algorithms can be made as learnable or as unlearnable as you want as a designer of that algorithm. And this really depends on the problem itself, like your domain knowledge, how hard the problem is to solve, how fast it is, how accurate it is, and whether you think neural networks will help it, or learning part of that algorithm will help you. And this is really great because it's combining the best worlds of traditional modeling and learning. So, we can balance the pros and cons of using a neural network with having much more interpretability, probably better generalization when we're using a fixed or traditional algorithm. So this is just the key idea you want to take away from this example is we can take any traditional algorithm and make it as flexible as we want. Okay. Yeah, so we can add learnable components everywhere. I guess the caveat here would be if you made the whole thing learnable, you would need an awful lot of training data to make it any good. So there is a balance here between flexibility and the amount of data you need to train on. So this is things you need to think about. And the availability of your data will probably inform your choice of what you want to learn in your algorithm too. So yeah, so for example, here's some other ideas. As I was describing before, you could have a neural network which gives you a starting guess of this code, rather than just taking some blurry idea. And that could be informed on the real data. So it could try to learn a direct map between the observational data and the start of the inverse problem. And then we feed that into our forward modeling afterwards. So that's one thing you could do. You could add, we were talking about this before, if you think the forward modeling is a little bit inaccurate, say that the detectors are in slightly the wrong place, or we've got the angle of the setup wrong, the setup of the actual experiment. We could learn a residual correction that tries to correct that based on our training data. We realize there's a systematic error in our modeling. Yeah, we can change the regularizer, and we can update the gradients. So yeah, as we were saying before. Okay. And as I said, all trained with the same loss function, where we're matching the output of the inverse algorithm with some true labels. trained across lots of example inverse problems. Okay. So we'll take a little break and then we'll get back to it.
Oh, good. We learn actually down on the steps. Yeah.
Yeah, so it's really hard. I think you really have to understand the problem.
Like if you actually want test one, two things, maybe good. Like actually the goal is more you have like somewhere in your laboratory a really good center.
Yeah.
Then you make all your good samples. Then you can deploy anyone that can correct. That's more
yeah. You just have to really understand the problems that you're trying to solve.
If you have set up a phone, then you want to deploy more machine learning and have all the data control. You can relearn it. Maybe all data you can relearn every place
yeah. So you think maybe if you have like a task that you've done, yeah. So what you feel like do some fine tuning, for example, and make a pre-trained model. So you could think of it as like swappable components into your hybrid workflow. If you have like a different model for a different machine, like that, then learn them jointly if you want as well. And if it's starting generalizing it across all sorts of fun stuff that you once you realize it.
It only needs to application.
The caveat here is it's like probably only perform well on the training data that it's in. So if you give it a fully new inverse problem, it might not perform very well. So it's expensive to train this as well, because the function is very expensive to get because you have to run it a whole inverse algorithm and just pick up one grade. And so you only want to do this where you know that you're going to have to run many inverse algorithms in the future, which are like similar types to the which thankfully is actually very free for any real problems. So for example, MRI people come with
the example cannot make sense because the test. Run and predict more populations.
So I mean, I think you've got it.
And here, I learned C++ and like Python is not really it's even not the programming as well. Like the way I read it,
Yeah, sure.
The second task from the day was this inverse from the clear temperature given and we compare the solution and I think you got quite similar images, but for us it doesn't make sense. physically, that's the temperature of the soil, distribution and environment. And also in the first part, we don't
you're not sure about the solution.
Yes.
Yeah. But like different approach, but it's all convergent, but it's the same thing. Singular. Yeah. It's this stuff. Yeah.
So it doesn't make sense that if you eat on this side with the fluid, then change more to the past. Then again, I don't know what problem was generated. We should expect.
Is this the steady state? It's a steady state. It's a function of time. Oh, it's kind of, oh, this is kind of, this is, yeah. Like kind of, yeah, I mean, after a correct solution, if the estimated the temperature matches the exact one. Like if this is truly the case, and you pass this model through your physics model, you've got this prediction, and you're sure that you use this, if you feel like the nice then it's going to, by definition, yeah. I'd have to do more about the information that does seem a bit. Yeah, it may be that. I don't know if we coded it. So I didn't design code, but I wonder if we coded it up so that it was supposed to be a full Gaussian, like Gaussian solution. I don't know if we might have done that on purpose. Yeah, if you both get the same.
Just now, is there any geometry of the solid?
It says
like that there are specific points that are there in the objects, and then it makes sense that when we.
I mean, I have to look it up on the definition. I can't remember much about it. I thought it was like a cylinder as well. And this is a representation of this direction of cylinders. Same
Times so heating.
Yeah, so if you start heating when the heats up, just go on this side.
But it's really that it would be also like if it's the physics
and you sure you've got your
has to be
yeah.
If there is an error, then it must be.
Yeah, exactly. Are you sure you've got your boundary conditions set up with your physics? I would just double check your effects.
Okay, if you could take your seats, we'll get back to this. Okay, so we recapped differentiable physics, hybrid workflows. I did a little coding example for you, and then we've looked at a much more complicated idea, which is integrating learnable components into an inverse algorithm. So combining gradient descent on top of gradient descent. So, and hopefully you can see that we can just arbitrarily add learnable components to our traditional algorithms to improve them. Okay, so I'm going to now move slightly and talk about a related field, which are neural differential equations. But as you hopefully see, this is also could just be thought of as a hybrid technique, where we're learning learning components of differential equation solvers, so of simulators. But it is rightly its own field, and so we're going to talk about it as a field as well. Okay, so we're going to just think about ordinary differential equations because they're the simplest to kind of study and think about. So what we've got at the top here is a very generic, general description of an ordinary differential equation. We have x here as a vector, just depends on a single value of time, and its gradient is dependent on this function of x and t here. And so, yeah, many physical systems are obeyed by ordinary differential equations, and this is just one example of the Lotka-Volterra system. So I'm sure most of you have probably seen this before. This models predator-prey dynamics in a biological system. And so x here is the population of the prey, and y here is the population of the predator. And we just say their rates of changes, so their birth and death rates, essentially, as a function of time, depend in a non-linear way between the population currently and then the population of their predator or prey as well. So there's a crosstalk between the two population densities. Yeah, there are reasons why you would choose this particular structure. I'm not going to go into it. We're just going to think of it as an ordinary differential equation that's interesting to look at. So, and then this is just an example solution. If you choose these parameters here, so this alpha, beta, gamma, delta, which just tell you what the max birth rate is, the effect of the predators on the growth rate, etc. This is the type of solution you get, and you see that the predator dynamics both the dynamics are cyclic, and the predator dynamics usually just lag a little bit behind the prey dynamics. So once you've got a spike in prey, obviously the predators have a lot of food to eat, and so they grow afterwards. So this is the model. Okay, so this is an ordinary differential equation. There's nothing fancy going on here. This is like standard physics modeling or biological modeling. So what is a neural differential equation? Well, so we asked the question, what if we're unsure about these functions? So we don't know if we actually have this functional dependence between the growth rates of both the predator and the prey. So what if it's not x times y? What if it's like x times y squared or some other law of the system that we don't actually know? So we're talking here about essentially equation discovery, like understanding the equations that govern some physical system. Okay. So what is a neural differential equation? It's just a differential equation which has neural networks representing some of the terms or operators perhaps inside of that differential equation. So we say, okay, we're not sure. So we say, okay, we have this model for the prey's dynamics. We know that it depends on the prey, but then it has some other nonlinear term that also depends on the predator, but we're not actually sure what it is. Like it could be XY, but maybe it's something else. And so we're just going to replace that with a flexible learnable function that we're going to try and learn from some data. So we're going to say, yeah, we have neural network as a function of XY with some flexible parameters that will allow it to learn. And the same thing with the predator dynamics. We can also assume, there's some neural network here, and then maybe we're not sure of the value of the growth rate of the predators here, so we could treat that as a learnable parameter too, based on some example data. Okay, so this should be ringing bells with the hybrid methods that I've been talking about before. It's kind of a similar idea where we're taking an existing model, adding learnable components to it. Okay. So yeah, this general idea of putting neural networks into your differential equation is a neural differential equation. So what we're going to do is we're going to define a hybrid approach to be able to learn these neural networks. So that's the goal of this, is to understand what these underlying differential equations are. So how are we going to do this? So one way we could do is to solve the differential equations. And a very standard way of doing this is to use the Euler method to discretize this ordinary differential equation and learn what x is as a function of t. And so we just approximate this derivative with a finite difference derivative. So x at time plus 1 is just x plus the time step with the evaluation of this function at the current state. So this is, this probably the simplest method of solving this differential equation you could think of. So this is for the general ODE. If you just think about this Lotka-Volterra system, again, I'm just rewriting this, but putting in the exact forms of the equation here and separating it out into x here is a vector in general. So we're separating it out into the x and y components of that vector explicitly here. So this is for the base equation. And then if we have this normal differential equation, which, we're replacing some of the terms with neural networks, we can still solve this differential equation. The function evaluations that we're doing up here now just become evaluations for the neural network, because the neural network is just a mathematical function, just as x, y is a mathematical function. There's no difference. So this is how you would solve this neural differential equation. And it's an update step. Well, this algorithm eventually is going to be an iterative algorithm that's going to, compute x over multiple time steps. And it's going to have some standard manipulation, mathematical manipulation here, and it's going to have some neural networks inside of it. And so you can see that this is starting to look very much like a hybrid algorithm that we've been talking about before, where we're messing around with a physics solver. So yeah, this would be the pseudocode. Again, I'm writing all of these hybrid algorithms in the same pseudocode structure to make so that you can realize how similar they are. They're just functions with inputs and outputs. And so this function now is just, the input, the initial population of the predator and the prey, x and y0, our time step and the values of the neural networks, which we're trying to learn the parts of the differential equation. And then we have this time stepping algorithm, which is just implementing this Euler solver. Okay. So yeah, it should be pretty clear to you that how we train this, but it's exactly the same ideas as we've trained all the other hybrid approaches. Is we just think, what are the inputs and outputs of this function? So the inputs here are initial values, and so we're just going to fix them at 0.2 or 0.5 or something, and then 5 or 4.5 or something. And we pass it through, we get a prediction of the solution through time. And then we just match that prediction to the observed values of the solution. So let's say that we have these black data points here, and we're going to try and learn theta so that the solution of the differential equation matches those observed data points. So this is a hybrid workflow. It's much simpler than the inverse workflow that we were talking about before, but still it's the same idea. Okay. So yeah, this is the cool thing. So this paper looked at this exact problem and used a neural differential equation to model this system. And yeah, this was the example data points, these green and orange points of the predator and the prey populations. And then you can see the prediction of the neural differential equation, or the hybrid solver, matches those data points very well. And so what that's saying is the neural networks have learned or approximated that XY function inside the original differential equation. So yeah, so now once we've trained the system, we have these neural networks, and one extra step that we can do is we can do symbolic regression on each of these neural networks to effectively discover what this underlying equation is, like analytical equation. So there are actually many symbolic regression algorithms out there that you can use, and that would help you realize that this neural network is just approximated x times y. I mean, if you just plotted the neural network output as a function of x and y, you would probably see, if it was a simple curve, you might be able to relate yourself, oh, it's learned x times y. So yeah, this is how you would use like a hybrid technique to learn about or just discover the equation if you didn't know what the equation was. And obviously this could be applied to many other differential equations, not just ordinary differential equations. Right, so what's really cool about this is this. So what we're doing here is we're plotting the solution, so the solution of the differential equation for later time steps. So remember, we only trained the model, these neural networks, on these first time steps here. But then we're going to run the solver, the hybrid solver, over many more time steps when we're just evaluating it. We're not going to train it any longer. What you see is that this model generalizes really well, and it predicts the cyclic dynamics for basically an arbitrary number of cycles. Like it's nailed the model. So why is this? Why is this model generalized so well? What's the reason?
We try to follow the differential equation.
Yeah. Someone else maybe as well. That's what you were going to say, that, I guess. Yeah. So exactly. So this model is very constrained. Like, we're not saying the neural network is. So imagine if we trained like an RNN, for example, on this data and just treated it as a time series. We didn't have any assumption about the underlying differential equation. It's just, a neural network which takes in the time series, predicts a new value. What you would nearly always find is the RNN would be able to predict the training points well, and maybe generalize to like maybe a couple of cycles, but then there would be accumulation of error and it would probably blow up eventually. And this is the generalization issue of neural networks, that they perform well within their inputs, but badly when their inputs are outside of their training distribution. So it's actually really cool that this model like generalizes outside of its training data, if you just think of this as a machine learning model. And yeah, it's exactly because what you said, the neural network is contained inside a very constraining system of differential equations that really constrain the types of solutions that it can model. So this leads us to another question or another idea, which is, why don't we just use this whole thing to model other data sets, and not just physical data sets, but like any data set? So why don't we use this, neural differential equation and the solver that we just defined to model like arbitrary time series that, say if we had another time series that was cyclic, maybe it didn't represent the predator-prey dynamics of a biological system. Maybe it was like the temperature of the Earth as it varies through the season. Could we use a neural ODE to like learn that, and would it be able to generalize way better than, for example, like an RNN or like just a standard out-the-box neural network? So this is a really cool idea. We're now starting to bridge from like using SciML for scientific problems, and we're now starting to use SciML for computer science problems, or like pure machine learning problems. So this is a really, really cool idea. Can we use differential equations to like model other data sets that are maybe not just physical data sets? So yeah, let's just draw it out in a very simple like idea. What we have in the middle here is like our PDE solver. Like that hybrid algorithm we used was just an Euler solver with some learnable neural networks in the middle of it. So instead of having biological data, why don't we just have any other type of data that we want to learn the mapping between? So for example, MNIST, with this classic problem in machine learning. Can we classify digits, handwritten digits? So our input here, remember, this is just a function, essentially, this is just an algorithmic function. It takes some vector as input, and so this vector could just be the pixels of the image. And it produces another vector as output. We could just say it's a scalar vector, and it represents the probability that image is a 7. And then we're just going to train, again, we're going to train these neural networks inside of this differential equation to try and match between the inputs and outputs. Okay, so in this way, from a machine learning angle, we can actually think of the PDE solver as just a custom neural network architecture. Like we're replacing a ResNet or a CNN or fully connected network here, which we would normally use to solve this problem, with like a PDE solver with flexible parameters. But you could just think of that as like a custom neural network architecture, as like an analogy. Okay. All right, so we're going to delve into this link a bit more. And what we're going to find is that neural network architectures some of the ones that we know and love can actually be thought of as solving differential equations. And this link actually goes much deeper than you think. Like that there's a very close connection between differential equations and neural networks themselves. So let's step back and think about this ordinary differential equation that we had in the start. So again, probably a very general way of writing an ODE. And it's exactly the same as I had. I've just said now we're going to treat this function as a learnable function. So it's going to have some free parameters theta. So it could be like a neural network, for example. And this is the thing that we're going to try and learn. So just imagine again solving this differential equation with an Euler method. Same thing. We just take the current state. We add the time difference with the evaluation of the function to solve this differential equation. Again, it gives us x as a function of t using whatever this flexible function is. Okay, so if you stare at this long enough, or what you can do is draw this out as a graph. So you say, okay, I've got a vector here as input, passing it through this function, getting an output, and I'm just adding it to the original input. This is exactly what this operation is doing. And so if you stare at that long enough, you realize that this is exactly the same as a residual layer inside a ResNet. So this is exactly what a ResNet does at each layer of the ResNet. It takes your hidden state or your hidden vector, passes it through a neural network layer. This could be like a fully connected network. It could be whatever you want, a CNN, adds it to original input and gets your next thing. And then the ResNet is just composed of lots of these residual layers. So it should be really clear to you that the ResNet is an Euler solver. It's actually solving this differential equation. If you think of lots of these steps combined together, in fact, think of like an infinite number of layers, like an infinite number of steps. That's equivalent as saying I'm taking the time step of my Euler solver to be smaller and smaller, and in the limit, the ResNet is truly computing the solution to this differential equation. So the input to the ResNet would be x at t equals 0, and the output would be x at t equals some final time. This is without changing the ResNet at all. This is just interpreting it from a differential equation perspective. Hopefully that makes sense. That's like a really cool, interesting kind of bridge or concept to get your head around. Right. So let's try and take it a step further. Let's think, we used an Euler solver, but there are actually like many different ways to solve this differential equation. So we have Runge-Kutta methods. So Euler solvers like a basic Runge-Kutta method, but there are other higher order methods that are able to solve this more accurately by doing a bit more computation. So for example, this is the base step of a RK4 method. So this is the fourth order Runge-Kutta. It's the same idea. We're just computing the next time step of the solution given the previous time step. But now we're doing this higher order approximation, which evaluates these different coefficients, K1, K2, K3, K4. And they're just functions of the input, x, I, with various perturbations. And you can think of this as like approximating or getting the gradients of the function. You can look at how the Runge-Kutta method works. I'm not going to go into exactly how it's working. So let's do the same thing. Let's take this basic update and just plot it as a graph. So we say, here's our input, incoming thing. Here's our output, the next time step of the solution. And then we're just passing it through these functions here. And we've got, if you see here, we've got lots of additions here. So we're adding all of our intermediate coefficient computations to our output here. We're adding K1 to Xi here, so we're adding a thing here. So from a machine learning perspective or neural network architecture perspective, this is just essentially like a custom residual block. It's like a residual block, but like a little more complicated. And I mean, when you look at sophisticated neural network architectures, they often look like this, where you have, it's more complex than just a residual connection. They have lots of interconnected connections in the neural network architecture. Okay, so what you realize is other solvers. So we have the same differential equation here, but we're defining a different solver to solve the equation. And so what we see is different solvers give you different neural network architectures if you're thinking of the PDE solver as a neural network architecture. So this is also really interesting. Like different architectures could be solving the same differential equation. It just depends on how the equation is solved and how it is discretized. This is the fundamental thing. Cool. So yeah, there's this paper, a very famous paper called Neural Ordinary Differential Equations, presented at NeurIPS, and they proposed exactly this bridge between ResNets and interpreting ResNets as Euler solvers and solving ordinary differential equations. And so they trained just a standard fully connected network to classify these digits, these endless digits. They compared it to a ResNet, and then they compared it to this RK-net, which is using a Runge-Kutta solver to solve this underlying differential equation instead of Euler solver. And you could also use many other ways to solve the differential equation and compare its accuracy when learning to classify digits as well. So a really fascinating paper. I definitely recommend reading it. So yeah, long story short, the accuracy was fairly similar, but it is very interesting in general to compare it on different methods and just to use this interpretation of neural network architectures being PDE solvers to help us understand neural networks. So the final thing we're going to try and do now is see if we can take a convolutional network and figure out if that's trying to solve a differential equation, like if there's an underlying differential equation that CNNs are trying to solve. In the same way that ResNets solve ordinary differential equations, what does CNN solve if they were to solve a differential equation? So this is the kind of question that we're going to ask and try and answer. So we're going to do a really simple problem. So we're going to just say, we're going to have a 1D convolutional layer. So this is a standard convolutional layer used in machine learning, where you have just a vector as input. So this is yi. And then the convolutional layer is just defined as a convolution of your weight vector with the input vector. And the weight vector, we're going to just say has 3 values. So theta 1, theta 2, theta 3. So how does the convolution work? Let's just remind ourselves. So to evaluate the value of yi plus 1, so that the next state of the output of the convolutional layer, we just do a convolution of the weight matrix with the input. And so we take theta 1 times this value of yi, theta 2 times this value, theta 3 times this value, then we sum them together and we get the output of this vector. Okay, so basic convolutional layer. All right, so to go further, we're going to do a little. We need to do a little trick, and this is as follows. So we're going to transform theta into a new vector. So we're going to say we have this new vector beta, which also consists of 3 elements. Beta 1, beta 2, beta 3, and it's just a function of the original theta here. And the value of this function is just given by this matrix equation. So to figure out what B1, B2, B3 is, this is just AX equals B. You just need to invert that matrix equation. You need to invert this matrix and you'll get an expression for B1. So I've chosen some fairly, it seems like arbitrary numbers inside this matrix here with this value of H. So we're going to interpret H here as the spacing between the elements. So if Y here is actually a function of X, H would be the spacing of when we've discretized Y, what's the spacing of each of the Y values. So it's going to become clear why we chose these numbers in a minute. But the other thing I'm going to just assume, which is true, if you analyze this matrix equation, is that these beta values are uniquely determined by this matrix and these theta values. So that there's like a unique solution, and you can use standard matrix algebra and look at determinants, etc., to prove that. As long as H is greater than 0. Okay, so this seems a bit complicated. So why are we doing this? So the reason we do this is so that we can rewrite this convolutional operator. So instead of saying it's theta involved with this, we can now decompose theta into the summation of these 3 vectors. So if we added these 3 vectors together, we would get back to theta 1, theta 2, theta 3. And you can see that just from the Mace equation, right? So if I take just the first element of theta 1 here is this row times by this column, which is this value times by this value added to this value and this value. So you can see how theta 1 is represented. Okay, so what's cool about this is we've turned this from like an arbitrary convolution with these weights could be any values, anything at all, to a convolution, to a set of 3 convolutions where the weights are now fixed. They're like fixed values. This is -1, 2, -1. These are no longer like free parameters. The free parameters are now contained in the coefficients of these convolutional layers rather than the weights of the convolutional layers. So the final, like a final value that you scale the output by. Okay. And so what you can realize is if we look at this, so let's look at this particular convolutional filter. We're taking -1 of this, none of this one, and 1 of this, and then we're summing them together. And what exactly is that? Well, that's exactly a derivative of yi. Yeah, we're taking the difference of this with this one. This approximates the gradient of this. The gradient of y is a function of x. And if we interpret h as the spacing, then in the limit of h going to 0, this is exactly the gradient of y with respect to x along this direction. So in the limit, we can start, we're now starting to form our differential equation that this CNN layer is like computing. So we replace these convolutional filters with gradients. So the first one here, this is basically like a weighted sum around the middle value, which in the limit will just become the middle value. So this is just passing the same value through. So y here times by this beta coefficient. This one here, we already realized is the gradient. And then the final one here, you can stare at that and realize that it's giving you the curvature. So the second order derivative with respect to x. So this is in the limit as h is going to 0, we realize this update is actually computing this differentiable operator. Okay, so the last thing we can do is we can say, let's think about a residual convolutional network. So this is where we have this convolutional layer, and then we also add to the output the input value. So we add a residual connection, very similar to how a ResNet is working. So it would be yi plus 1 equals the convolution plus yi. If you do that, that just adds yi to this extra update here. And that is just a kind of, if you do that, then we can move yi over to the left-hand side. This becomes a difference. And again, in the limit of like an infinite number of residual convolutional layers, we can get to, we can say if along this direction is a time axis, in the limit, this becomes a derivative in time. Very similar to how we interpreted the ResNet as solving a time equation. And now we've ended up at a differential equation. So what we're saying is, residual CNNs solve this partial differential equation. So it solves for y, given some initial value of y. And the learnable parts, so this is a null differential equation because we have some learnable parameters inside the differential equation. And the residual CNN solves this null differential equation. And the parameters of the network turn up in the coefficients of each of these terms in the equation. So this is a really, really cool way of interpreting, CNNs. And this paper is a really fascinating paper. Again, it's worth reading. And it looks at other architectures too, and the types of differential equations that those architectures could be interpreted as solving. I mean, once you have this, then you can start dreaming up some cool ideas. You could say, well, what if the data should be obeyed by a differential equation which doesn't have this first order gradient term in it? Maybe it just depends on its second order gradient in x. So we could just get rid of this and fix the values of beta 2 to be like 0. And that would define, if you reverse it back into a neural network architecture, that would define like a new type of architecture which solves like a slightly different differential equation. And so this paper, for example, proposes parabolic CNNs, which does this type of idea. And so, yeah, at the end of the day, you can see that there's this really cool bridge between like differential equations and their solvers and neural network architectures. And you can take, like, we have rich understanding of both of those different fields, and we can take insights to help both sides of that equality. So, you know, for example, Poisson equations, Laplace equations, wave equations, we have a rich understanding of how to solve those equations, the types of solutions that they model. We could put that into designing good architectures that work well on certain data sets, for example. Or take it the other way, we know of some really amazing architectures like transformers and residual networks that seem to work better than others. Can we interpret those differential equations, and what does that tell us about PDEs? And also, if we know something about how well those networks train, does that help us design like a better differential equation solver, for example? So yeah, this is a super fascinating link, and I think it's a really nice way to like finish the kind of course, is to show you that these fields are really, really related and really linked together. Okay, so I've just got maybe 2 more slides where I'm just going to try and summarize the whole course, because we're now at the end of the course. And we're gonna really step back and think about what I was talking about at the start of the lecture, start of the course. So throughout this course, we've been talking about scientific machine learning, and what we said is, you know, if we just apply machine learning naively to scientific problems, we start hitting these problems like the lack of interpretability, the poor generalization, the amount of training data that we need. And it doesn't really fit right with us that we know we have all this vast scientific understanding, but yet the neural network is seeming to throw away that. And so all the methods that we've been talking about throughout the course is based on this kind of thesis or like hypothesis that if we add scientific understanding like more tightly into machine learning, we can produce models which are more powerful and more robust and more interpretable, and ultimately to, you know, help us push forward scientific research. So yeah, this is my summary of just some key like trends that I think you should just take away, that we've seen through the examples that we've been looking at. So I'm just going to talk through each one. So incorporating scientific understanding nearly always improves the performance of machine learning algorithms. So we see this time and time again, that if we add some physics constraint into our ML algorithm, it's generally going to be easier to interpret, and it's going to generalize better typically, and often requires less training data. As I've shown you in this lecture, SciML, especially hybrid methods, can be as flexible or as inflexible as you want. And this really depends on your problem. You have to be, this point at the bottom here, SciML requires interdisciplinary research. It's really hard to do good SciML because you have to be an expert in machine learning, but you also really have to understand your domain and the types of problems that you're trying to solve to choose a specialist technique that really works for that problem. So yeah, there are many different SciML approaches out there. We've talked about FNOs, talked about pins, we've talked about neural differential equations. There are many others that we just haven't had the time to talk about in the course. And so there is by no means a one-size-fits-all model or approach that you should be using. And even though we're using neural networks, we've seen that the techniques we've studied have their own limitations, and they still suffer from the limitations of neural networks. So it's all about understanding the pros and cons and using the right technique at the right time. And yeah, hopefully we've convinced you you can apply it to these general types of problems. So simulation, inversion, data assimilation, equation discovery, and we've given you examples across many different fields as well. So yeah, let's just go back to the learning objectives. So what I hope we've shown you is, or you now have a better understanding of the applications of deep learning and how we can put it into scientific computing, and not just in a very simple, naive way. You understand how to actually implement these algorithms. We've done coding exercises, tutorials to really understand how they work. And we've tried to be real with you about that deep learning is not going to fix everything, and we have to understand the limitations still. And there's some really important concepts, like, for example, auto-differentiation as being a key enabler of SciML, that are really important to take away. So that's the end of the course, and thank you very much for listening and being here. So, yeah. Thank you.